Hi everyone and welcome back. So today we're going to continue our study of nonlinear first-order systems by introducing an extremely useful tool called the phase plane. It's basically a different way of looking at solutions to these differential equations that should help us to understand their qualitative behavior in ways that are often the main thing that we're trying to find anyway. So to begin, we're going to simplify our notation to some extent. A two-dimensional autonomous system takes on this form. y1 prime equals f1 of y1, y2, y2 prime equals f2 of y1, y2. But when we're going to be looking at 2x2 systems, and to make life simpler, we're just going to relabel y1 as x and y2 as y, and f1 and f2 are going to be called f and g, right? So we can rewrite the system as x prime equals f of xy and y prime equals g of xy. And you're going to stick with some standard notation. It's going to be pretty useful for us. All right, so it turns out that it's often very useful to plot the solution curves to this system of differential equations in the xy plane, rather than, so if you recall, if you solved a system like this, you would get x of t equals some function of t, and y of t equals some function of t, and then you could plot each of those against t, and you could even put them on the same set of axes. That would be fine. And that's great. But often what you're concerned about is the relationship between x and y, not so much the relationships of each of them individually with time. And that's especially true in autonomous systems where the system doesn't change with time. So the only real thing that's changing the values of the variables is the other dependent variables. So x and y are influencing each other over the course of time. So we'd like to see how that interaction works out in a way that's kind of free of the context of the specific times. So we're going to be looking at the xy plane, and when in this we're going to be plotting solutions, their x and y values together to give points in this plane, and then they're going to trace out curves as time changes. So the xy plane in this context is called the phase plane. And we will be looking at this. A more general version of this when you have higher dimension is called phase space. Okay, so we're going to be looking at the phase plane. What's going on here? Well, you consider the xy plane, and before, we suppose we don't have a solution for the differential equation. What we can know is that for every point in the plane, we could figure out a velocity vector, right? Because we have a differential equation that will tell us how fast is x changing and how fast is y changing at that point in time. So every point in the xy plane has associated with it a velocity vector that we could also plot on the plane. What is that velocity vector? Well, let's take a look. Suppose that we have a solution and it passes through a point x bar, y bar, right? Borrowing the notation from the book. So then x of t, y of t equals x bar, y bar at that time. What's the velocity at that time? Well, the velocity is the vector that's made up of x prime of t times y prime of t, right? This is a parametric representation. So if we do it in the ij notation, that's x prime of ti plus y prime of tj. And the book does that a fair bit too, so I wanted to include that. I tend to like to put them in like points, coordinates and points. Okay, so in any case, x prime of t, we know is equal to f of xy because it satisfies the differential equation. So we could replace x prime with f of x of t, y of t. Similarly, y prime can be replaced by g of x of t, y of t. And of course, x and y we know are x bar, y bar. So what we see here is that the velocity vector v can be written in terms, all we need to do to write it is we have to know x and y, so we need to know where we are in the plane, and we need to know f and g, we need to know the differential equation. What we don't need to know is what time it is. We don't need to know t in order to figure out the velocity vector. It only depends on x and y. And that's why this phase plane idea is going to be so useful, because whatever the velocity vector is at a particular point, it's always going to be the same, no matter how much time elapses. It's not time dependent. Okay, so let's take a look at an example of what velocity vectors in the phase plane look like. So this is the competing species model that we've talked about last time. And I've given the phase plane here from 0, a little less than 0 up to about 2.5. And what you'll see here, the red dots, these are the equilibria that we figured out last time when we did this exact same example and we found the equilibria. So we have 0, 0, 2, 0, 0, 2, and 2/3, 2/3. So those are our equilibria. And we know that at those points, the velocity will be 0, right? Because at those points, f is equal to 0 and g is equal to 0. At all of the other points, we're going to have one of those components be non-zero, so we're going to be able to draw in a vector. And that's what has been done here. So all of these points have a vector, and that vector's direction and length have been determined by the differential equation. So if you wanted to generate this figure, you would go through at all of these points, and then you'd figure out the x and y coordinates. So say like at 1.5, 1.5, you would plug them into your two differential equations. That would give you the x component and the y component of a velocity vector, and you could plot them in there. Now, as you can see, these arrows have different lengths because the vectors might have different magnitudes. That's usually not such a great concern. You can imagine how this could get pretty ugly. Like if these vectors over here were very much longer, then they would be bumping up against each other, running over each other, potentially crossing each other. It gets very confusing to look at. So what we often do is we simplify this picture by, instead of drawing in the vectors, we draw in little line segments with the same slope as the vectors. And so you can give them some direction. You can point an arrow whether it's going to the left or to the right. That's pretty useful. But this is that same vector field that we just saw here, but now with everything drawn with the same length, right? And it doesn't have the arrowheads on it, but that's just a limitation of the graphing software that I used for this. So it makes it a little bit easier to see what's going on, though. So you don't have the tiny arrows over here on the right-hand side. You don't have these huge arrows on the right-hand side. Everything's pretty steady. So, but this gives you an idea of what the flow is, right? Because what does solutions have to do? These are velocities for solutions. The velocity has to be not perpendicular, has to be tangent to the solution curve, right? Velocity is always the rate of change of the curve, which means it is the tangent line or the tangent vector. So any solution curve has to find a way through the plane, right? So say I had an initial condition here, then a solution would have to find a curve through the plane that manages to stay parallel, tangent to all of these curves at all times. So it's going to be dictated by those directions, which direction the curve has to flow. And you can see there's a few different things going on here. It would be nice to see some solutions. So I've numerically figured out some of the solutions, and we'll see those on the next slide. So solutions to the differential equation appear as curves that are always tangent to the vector field that we've put in. This has a few more arrows in it, but this is a bunch of different solutions. Each of these curves, each of these blue curves represents a different solution to the differential equation depending on where you start. Now, one of the nice things about these systems is because of theorem 6.1, we know that we have unique solutions at points on the plane as long as all the partials are continuous and things like that. Because they're unique solutions, we know that no two solution curves can intersect each other, because if they intersected at a point, that would violate uniqueness. So we must have all of these curves are going to be going through the same phase plane, but never intersecting each other. And that's what really allows us to analyze, using some geometry, what happens in with autonomous systems by looking at the phase plane. Right, so one thing you can't quite tell with these solutions is basically you start at a point, any point, and then this curve represents how that point will move with time. Right? We don't know how fast or slow, but this solution, right, would be changing. The x and y values would be changing in this way as time proceeds, and then it would continue like this. Right, you can see the long-term behavior. It looks like it's going to be converging toward that equilibrium value at the top. Right, so you need to know a little bit about direction to figure these things out. Whereas if you started with an initial condition down here, in the near the 0, 0 equilibrium, right, then things will move up. So the x value will be increasing and the y value increasing for a bit, then the y value will start to come down, and things will converge toward this equilibrium. This actually has some interesting things to say about ecology. This system represents two competing species, and what we see here is that depending on the initial conditions, some initial conditions lead to the population going entirely toward the second species, that's at 2, and the x1 is at 0. And some initial conditions lead to the opposite conclusion. This is the concept known as competitive exclusion. So depending on the initial state of the system, one species or the other will dominate. You're never going to arrive at the coexistence state that exists in the middle there. All right, so one more tool that we can use for understanding what's going on in the phase plane is what's called Null Clines. So as you can probably imagine, drawing in all those arrows is a pain in the butt. You don't want to do it. It's a lot of work. You don't know how many points you need. It can be hard to read all of those arrows and know kind of what the overall flow of how solutions are moving is. It's tough. It is tough. So instead of doing that, we want to have some kind of big picture idea of what's going on. We have this tool called a null cline. A null cline is a curve in the phase plane along which either f of x or g of x is equal to 0. So on these curves, the velocity vector is either going to be vertical, right? If f is 0, right? If f is 0, that means that the rate of change of x is 0, no left-right change. That means the velocity vector must be vertical. If g is equal to 0, then the velocity vector will be horizontal because there's no change in the y direction. So we want to treat these two types of null clines separately, kind of the vertical one and the horizontal one. And basically, these curves are going to mark out in the phase plane the places where a solution curve can possibly change direction. The only way you're going to be able to change from going from the left to the right is if you pass through a point where you're not doing either, where the horizontal rate of change is 0. Similarly, if you're going to change from going from up to down or vice versa, you need to pass through a point where the rate of change of y is 0. Those are exactly happening on the null clines. Those are all of those possible points. As an added bonus, if these two different types of null clines intersect with each other, then you have a point where f equals 0 and g equals 0, and that's exactly an equilibrium point. All right, so let's try an example of this. The same example, there's our equations again. What are our null clines in this case? Well, there's two sets, and again, we want to treat them separately. So our first set of null clines come from the x equation. We are trying to find curves where this equals 0. So x equals 1 minus 1/2 x minus y equals 0. And we saw before when solving for equilibria that either means that x is equal to 0 or that y is equal to 1 minus 1/2 x. And these two things are null clines. That's the curve x equals 0. That's a vertical line on the y-axis. And y equals 1 minus 1/2 x. That's another null cline. It's another line. Right? Similarly, what are our null clines over here? We have y times 1 minus x minus 1/2 y is equal to 0. So that means either y equals 0 or 1 minus x minus 1/2 y equals 0, which translates to y equals 2 minus 2x. Again, these are null clines, but let's use a different color here because it's a different type, right? And then this is also a null cline. Okay, so what good does this do us if we plot things on the phase plane? If we throw in the null clines, here's what we get. There are our null clines, and again, it's good to plot them in a different color so you know that which one is of which type. So the pink ones here are x null clines, right? So pink is an x null cline, right? And that means that everything on those will be vertical. And then orange is a y null cline, and that means that the vector field on those will be horizontal. And we can figure out what direction things are going using a little bit of continuity. So for example, on the orange, we could take a point down here, right? Say that's 1/2 0, 1/2 comma 0, right? And plug it into the other equation. So 1/2 comma 0, let's see, into this equation. So we'd get x prime equals 1/2, 1 minus 1/2 times 1/2 minus 0 is 1/2 times 3/4. So the important thing is that it's positive. So going over here, we could say, okay, well here the arrow is positive. So that, and it turns out that all of these have to continue to be positive. The only way they can change direction is when they cross a null cline of the opposite type. So once that happens, then these start pointing in the other direction. And that continues as it kind of goes around the corner here. These are pointing in this direction. These are pointing in this direction. Right? And then we can do the same thing with the pink null cline. It turns out that if we plug that in, we get that things are moving up here, still moving up, up, and they switch to point down after that. And then this continues, these point up, and they switch when they cross the other null cline, and things point down. So what good is all this? Well, this gives us, this subdivides the plane into different regions where things are moving in different directions. And that turns out to be very, very useful. Get a few extra lines in here, extra arrows. So what this means is that, so for example, in this region here, what direction are the vectors pointing? Well, on the boundaries, they're pointing to the right and up. And by continuity, it turns out that everything in this region has to be going, I said to the right, I meant to the left and up. It turns out that everything in this region has to be going left and up. Out here in the big region to the right, we have indications that things are going to the left and down. So out here, everything has to be moving down and to the left. Right? Terrible arrow, but you get the idea. Similarly, in this region, everything has to be moving up and to the right, and in this region, everything has to be moving down and to the right. And that gives you the broad brush strokes of what solutions are doing. Right? You can tell the solutions are roughly going to come in this way, right? And then maybe they reach this line, then they start going up. Right? So you get solutions look like that. If they hit this line instead, then they have to turn around and go this way. Right? Solutions here go up and to the right, right? And when they do that, they might hit this wall, and then they have to start going down. Or they can go up and to the right and hit this, and then they have to start going to the left and continue going up. Right? So different kinds of things. You can tell the overall picture of what's going on just by drawing in these 4 lines in this case. You get a very good picture of the overall behavior of the system from that minimal information and from putting the arrows onto the null clines, either up or down or left or right. And again, notice that when the null clines of opposite type intersect, right, orange line, pink line, you get an equilibrium. Orange and pink, equilibrium, equilibrium, equilibrium. However, when 2 null clines of the same type intersect, there's no equilibrium, right? Because that's only one of the equations being satisfied. Being satisfied twice doesn't count. You need to have both equations simultaneously satisfied. So when they cross of opposite type, that's when you get the equilibria, and that's why it's a good idea to keep track of them separately, to draw them in different colors, for example, so you know you don't spuriously think that this is an equilibrium down here at 1, 0, because it's definitely not. All right, and then let's take a look at how these null clines interact with the solutions that we saw before. Those are those same solution curves, but now with the null clines drawn in. So what you'll see is that indeed these lines at these points where the curves hit the line, those are exactly the points where they turn around, right? A turn from right to left or from left to right happens at every one of these intersection points. And similarly, on the orange curve, every time a solution curve runs into that, it turns around. Either if it's going down, it starts going up. Like these guys, all of these guys, when it hits the orange curve, and if it's going up, it turns around and starts going down. Right? So we see that kind of dynamic. So null clines are a very useful tool for figuring out the phase plane. Phase plane is an incredibly useful tool for figuring out the dynamics of 2-dimensional autonomous systems. We'll be looking at all the kinds of things that can happen. We'll do this with the pendulum, for example, and see what it has to tell us in the phase plane. There's a lot of stuff going on.